Yes. Anyone wants to summarize? We saw CNC technology, right? That comes under the domain of CAM. If someone was trying to say something. Okay, so we saw uh, how we are able to implement CAM with the help of CNC technology. We saw that the CNC, as we call it, computer numerical control, is a system that utilizes stored programs. So you have a program of instructions, right? Part program is what we call it, and that contains the instructions about the uh, geometry data as well, like which coordinates, basically the coordinates of the geometry, and also miscellaneous functions such as tool, right? Which tool to use and how should the tool move, and coolant, etc. All of that information in the program of instructions. So that is fed to the CNC as an input, and with a mini computer that is attached to that CNC, right? You are able to execute those instructions. That's what we saw, right? And we have several types of CNC technology. CNC technology is applied in different processes like grinding, milling, punching, turning, etc. And from 1960s, we have been using the CNC technology, and it's still the dominant method. We have now advanced functions, advanced features in CNC that we did not had earlier, like the inclusion of different axes, okay, 4-axis, 5-axis machines, etc. We saw the different elements of the CNC system, right? Input device, machine control unit in this example, right? We have, let me slide show. So you have an input device which gives the part program. You have the machine control unit, which is the CPU of this system. So it controls the motion data. It gives out the motion data to the driving system, which drives our machine tool. And there's a feedback device, which gives the different feedback for the machine control unit to know whether the motion data that was sent has been executed or not, and several different miscellaneous functions, and a display unit to display those, to display what the operations that are being performed, right? The functions we saw: machine tool control, in process compensation, improved programming and operating features, and diagnostics, right? We saw that how that tool offset, right? That the tool being worn away gives rise to that blunt nose at the tip of the tool. So how that, if we are able to give that offset to the CNC, then we no longer need to have changes in the part program because of that wear of the tool. Okay, so it should be able to compensate in process as well, and programming and operating features, as we are able to modify the program, and diagnostics about the different tool troubleshooting, etc. Right? You see, I was talking about the punch tape, right? I told you that earlier we were having NC, numerical control machines. So they were using this punch tape as a unit, as an input. Okay, so this is how it would look like, and those holes are being punched. That will be read by the there will be a setup, okay, to read that. So this was, you had to store this, and also if there are modifications in the part geometry, you cannot use this tape anymore. You have to go for a different tape again. Storage was a problem, even modification was a problem, right? And also the time taken to read that, right? It's a physical thing. So this is what is a punch tape that I was talking about. Okay. Okay. Advantages And firstly, let us have a video, then we'll discuss this. Okay.
If you've ever taken shop class.
Is the video visible and the audio audible? Yes. Yes. Okay. So we'll see this video that talks about the CNC technology. Okay, the different CNC machines and how those different, as I was talking about, multi-axis machines, right? How are they able to produce those complicated parts? Okay, we'll get to know that, and then we'll see the advantages and disadvantages. Okay, so this is halfway down. We already know some basics about CNC, right? So this is a good point to have this video.
In high school or watched an episode of How It's Made, you probably have some idea how lathes and other metalworking machines function. As technology and computers have improved over the years, a new high-precision computer-controlled manufacturing technique called CNC machining has spawned. CNC machines, or computer numerically controlled machines, are electromechanical devices that can manipulate tools around a varying number of axes, usually 3 or 5, with high precision per instruction from a computer program. CNC machining is one of two ways that engineers, machinists, or makers can generate a physical part from a computer design file, with the other being 3D printing, known as additive manufacturing. The contrast between these two techniques is stark. CNC machining, like other machining processes, is a subtractive process, where material is removed from a stock. 3D printing, on the other hand, is an additive process, essentially functioning in reverse. The first CNC machines were developed in.
Was that clear? That CNC comes under subtractive manufacturing domain, isn't it? Was that clear? Was that part that the additive manufacturing domain consists of 3D printing, right? That's additive manufacturing. You have parts that are built layer upon layer. In here, when we are discussing CNC, it is important to mention that CNC comes under the process that we are doing in CNC is nothing but subtractive manufacturing, right? As you can see, the material is being removed, isn't it? So that's the difference. Okay, and then
Sir, good afternoon, sir. This is Fatima, ma'am.
yes, ma'am. Good afternoon.
Now, is this an elective, sir? Is it for which year is this?
This
Which year
is
students?
third year, second sem, ma'am.
Third year, second sem elective, is it?
No, it's a core
Regular
core
subject.
course. Yes, regular.
No, why is the strength so less?
Yes, ma'am. Actually, the total strength is 49, but
Oh,
still, generally
yeah,
they are
more
in
than
20s
50%
only.
are absent.
Yes, ma'am.
But that is so bad. No, they have to know that these classes will not be repeated.
Yes, ma'am. I have been observing that as well, and
And if the CR is there, I think CR also should do something about it. Send messages to his classmates and yeah. Otherwise, because this is how we are going to finish the semester. Exams and all will be online.
yes, ma'am.
So students, please ask your friends to join these classes because you are coming. No, you can ask your friends also to come and join the classes. And all important classes are happening here. Even labs are happening. So yeah, so please carry on, sir.
Okay,
Sorry
ma'am.
to interrupt.
Thank you.
Yeah.
No problem. I'll just put a message in the group, okay? And then we'll continue. Okay. So that's the difference, right? Subtractive and additive manufacturing. So we are discussing CNC, that comes under subtractive manufacturing domain.
In reverse, the first CNC machines were developed in the 1940s and 50s and relied primarily on a data storage technique known as punched tape. The code to control the machines would be manually punched into a data card and fed into a system that would then interpret the data. Needless to say, these early machines were rudimentary and their functionality was limited. CNC machining technologies rapidly grew as technological capability only accelerated in the late 20th century, which brings us to how modern CNC machines work. As mentioned before, machining is a way to transform a stock piece of material such as aluminum, steel, or titanium into a finished product or part. CNC machines rely on digital instructions, specifically referred to as G-code. Before modern computer-aided manufacturing and computer-aided design programs such as Autodesk's Fusion 360 were around, machinists would manually write the G-code to control these machines. CAM programs today allow you to take a 3D model and automatically generate G-code that will drive the machine with little input. When you compare the capabilities,
You see, we had discussed that the CAD modeling is being used for downstream applications, right? One of the applications, what I mentioned was as a database for CAM, right? So that digital product definition that you have, the product that you have is in digital form, right? So that CAD file, okay, that CAD model is now being used for generating this part program, right? That is to be fed to the CNC machine. So earlier, as he was mentioning, we used to write it manually, all those part programs, either manually or those punch tapes, as was mentioned, right? But now, because you have CAM softwares, such as we saw Mastercam, right? Mentioned as an example was Mastercam. That's a CAM software wherein you generate the G codes and M codes, right? So that part program is where is what is being generated, and then that is being fed to the CNC, right? So from that, the CNC machine will start executing the instructions.
of automated CNC machining to the manual alternative like lathes and other machining techniques, you can start to see the benefits. CNC machines simply run faster at higher precision and accuracy while simultaneously allowing the transformation of a digital design into a physical part. CNC machines are precise and are measured in thousandths of an inch, referred to as thou. Standard machining can provide
You see, 1,000th of an inch, that's the US standard. Okay, they use inches, isn't it? We use millimeters quite often. And, but in US, I'm sorry, they generally use inches. So 1,000th of an inch, right? 1/1000th of an inch, they call it 1 thou. So all the values that he'll give now will be based out of that inches only, okay?
tolerances on parts around plus or minus 0.005 inches. Fine machining can produce tolerances of about plus or minus 0.001 inches, and specialized processes like polishing can offer up repeatable tolerances as tight as plus or minus 0.00005 inches. For reference, a human hair is 0.00069 inches thick. Now that we have the basics of CNC machining out of the way, we can start to dig into the intricacies held within. within. Many designs or specific machining processes require the use of multiple tools to make cuts. One tool doesn't function universally. For this, machinists will often build digital tool libraries that interface with the physical CNC machine. These machines, often costing hundreds of thousands of dollars, can automatically switch tooling when directed by their digital instructions, allowing for them to become manufacturing workhorses. Basic CNC machining will move one or two axes, referred to as the x-axis and the y-axis. You'll often hear the terms 2.5-axis, 3-axis, and 5-axis CNC machines, which simply refer to the degrees of freedom a machine can make cuts in. A 3-axis machine will move in the x, y, and z axis, whereas a 5-axis machine can move in these 3 axes along with 2 additional rotational axes.
Now, do you understand what that 5-axis machine means? Right? That is generally what we see for complex geometries. The word 5-axis machine is what is being used quite often. Those machines will have 5 axes. So in the sense, it basically indicates the degrees of freedom that are allowed, right? So not just they can translate in X, Y, and Z, they can also rotate about any other 2 axes, generally X and Y. So that is how they are able to, if you can observe, he'll show some, yes, a turbine component, okay, that turbine blade itself. When we are manufacturing that, how that tool moves, okay, tool rotates basically, okay, not just translates but also rotates. Doubt so far? Still there are 18 candidates only. No. Okay. Any other? No one has any doubts? Okay. So we'll observe that. Okay. Bye. Okay.
As you might be able to imagine, the possibilities of production with 5-axis machines are practically endless. 5-axis machines used to be relegated to hyper.
You see how that is rotating as well? That's what we were talking about. So that's rotation about one axis, or if it is moving like this, that's rotation about another axis. So that gives us the capability to machine these complex surfaces, right? To be able to form these surfaces which are having complicated curves, as you can see, and not just in one direction but multi-directional. Okay, so
precision work, but as they have become more affordable, they are quickly becoming standard in many shops. There are 3 conventional machining technologies that you need to understand to grasp the basics of how material is removed from stock in CNC machines. The first being drills. Drills work by spinning a drill bit and moving the bit into contact with a stationary stock. Next, we have lathes, which function in reverse to drilling. Lathes spin the block of material against a stationary drill bit or cutter to remove material in a circular or fluid path. The shape capabilities on lathes are more limited than other techniques, but modern technology does allow these machines to create things such as square holes or non-circular shapes. Lastly, the most common CNC machine type is referred to as a milling machine. Milling machines involve the use of rotary cutting tools to remove material from a stock piece. These machines function similar to drills, with their tooling capabilities encompassing much more variety. Almost any material can be used in CNC tools to remove.
you see, those are the 3 general CNC machines we have. Okay, generally in machining, basically you have drilling, isn't it, wherein the tool moves, okay, and the block is stationary, the workpiece is stationary. In lathe, the workpiece moves and the tool is you can say the tool moves, but it's not, it doesn't rotate, right? In here it rotates, okay, there it doesn't. it only translates. So that's turning. Okay, CNC turning, that's what we call. This is drilling, and that is milling. That's the most common, as he was mentioning, because it gives us a lot of options, right? To have multi-axis and to be able to create those complicated components. Okay. Doubts? You all have studied this in your manufacturing subject, right? The different processes that are there, traditional processes, and how we are. So this is what we are seeing is how we are able to do those processes using computer-aided technology. Okay. Okay.
Material from a stock piece. These machines function similar to drills, with their tooling capabilities encompassing much more variety. Almost any material can be used in CNC machines, from plastic to titanium. Different materials have different properties, so machinists and engineers will overcome their unique challenges by altering machining variables like tool selection, RPM, feed rate, and coolant flow, among an extensive variety of other factors.
You see all of these, as the material changes, you have all these factors changing, isn't it? The tool will change based on the material. If the workpiece is quite hard, okay, if the hardness of the workpiece is high, then you have to have a tool that is more harder than that, isn't it? Only then can you be able to machine that, right? Common sense. Also RPM, how that how with how much speed is the tool moving, okay? Or if it is a turning process, how much RPM is the workpiece turning. Feed rate, as we have seen, mm per revolution, how much the tool moves for every revolution of the workpiece. That's your feed rate. And then the coolant flow also, right? How much coolant should be given if a lot of heat is generated, okay? If you know that a lot of heat is generated, then the coolant flow will be a factor, right? It depends on the heat generated. So you might have observed when he was showing the milling process, that white fluid what you were seeing was the coolant, right? So all these will depend on the material, because each material has different properties. That's what is being shown, right? Okay.
CNC machined parts are all around you. They hold together your car and perform vital functions aboard SpaceX rockets. CNC machining is arguably the only way to produce high-precision metal parts for engineering designs across the world. If you're interested in learning more about CNC,
Okay, and that was about that video. Okay. Doubts in that? You see, those are the possibilities we have. Okay, no. So you see now the advantages. Continuous use. Unlike manual labor, CNC machinery, bearing any malfunction or maintenance issue, can work continuously over any period of time without a break. This greatly increases productivity and efficiency. So because they are able to, they are capable of continuous usage, right? Unlike manual labor. So yes, that's why they mentioned you do have malfunction or maintenance issues as well, but that's they don't occur quite frequently. Okay, so when that is there, then you have a then you can have a continuous usage, right? So that production rate will be increased because of that. And then consistency, precision, and redundancy. With computer software, the design of any given product only needs to be programmed once. The CNC machine can then perfectly replicate that design for any order quantity. So there is consistency. What do you mean by consistency? Yes, I think we that point came up earlier as well. Consistency. to be able to maintain same result. Yes, that's correct. So it should be what you can say in other words, uh, it should not change with time, right? That's what we call steady, right? In physics, we call steady or unsteady. Steady is something that doesn't change with time. So in terms of this, when you're saying the machine should be consistent, what we are seeing is the output of the machine should be consistent, right? Like it should not, the result should not vary, as he was saying. So each component when you're producing, okay, if you are producing a batch of, let's say, 20 components, then those 20 components should be same, isn't it? There should not be deviation in the dimensions, because essentially you're performing the same process with the same with you can say the same workpiece, right? There will be very minor deviation, like in maybe very minor, right? If you're dealing with micrometers, and if you're dealing with millimeters, then there will be very less deviations, okay, in micrometers or so. So if given that the input or the input workpiece is the same, the output of the machine should be same, right? Only then can you say the machine is consistent, and only then can you say that the products are standard. Because let's say those 20 components, uh, out of those 20 components produced, only 12 components are having the same dimensions, and the remaining 8 are not having same dimensions, okay, they vary. Let's say 8 are having same and 12 are having same, so there are two divisions now, in just one batch. So because of that, when they go into the market, if you are trying to purchase the same product from that lot and the other lot, okay, that 12 and 8, you will have a problem with the assembly, right? Even when you are saying that this is the same product that we are purchasing. So interchangeability cannot be there. You cannot just randomly pick any component. So that problem is there if you don't have standardization. And when can you have standardization? When you have consistency. You see how all those are connected. So the machine should be able to give consistent results, in the sense consistent output or units being produced. It should be precise also, right? Precision is you can say uh, is not with respect to time, but with respect to, you can say, um, how precise it is. Like for example, if we can produce within the tolerance range 0.1, okay, plus or minus 0.1. Another tolerance, let's say 0.01. 0.01 is more precise, right? If I need it for an application 0.01, okay, then for me 0.01 has to be produced, right? So I need more precise design, I can say, more precise components, sorry. So precision is also what we are able to achieve with CNC. As I said, with traditional methods, that CNC, traditional CNCs, I'm sorry, traditional lathes, you have a problem because you have vibration, you have operator error, okay, you have machine errors as well, right? The machine could not be, the machine is not having, what you can say, is not functioning properly. There are what you call is backlashes, right? The machine slides, okay, there's some gap in between tool post and the slide, for example, one example. So all of that will give rise to some defects in the product, so you will not get precise products, right? So precision and redundancy, so you will not have much wastage, okay? What you are trying to get, okay, is based out of optimal parameters that we have set. The CNC can then perfectly replicate that design for any other order quantity. Yes, another thing is because of the software, right? You have a program that needs to be written, right? And then the machine can process it. So instead of tapes, etc., only that program has to be generated in the software. Low skill requirement. CNC machines, okay, CNC machine operators require little training and skill when compared to manual machine operators. Is that correct? Is that correct or not? CNC machine operators require little training and skill when compared to manual machine operators. Yes. You see, in terms of, you see, if there is a lathe operator, okay, he has got the skill of moving that, okay, giving that feed rate, right? You see, there are, if you have observed in a lathe, you have feed rate and depth of cut, and there are skilled operators who operate both at the same time. Okay, with the left hand they operate the feed rate, and with the right hand they operate basically with that wheel, right? We have a wheel, isn't it? That's how we are able to change the feed rate and depth of cut. Rotating that wheel changes the depth of cut and feed rate. So multi-skilled skilled operators are able to do it both at the same time, right? So that skill is not required here. You see, that skill is now being performed. The computer is performing that operation, what the worker was performing, isn't it? So in terms of skill, what the skill that is required is to be able to handle that computer, right? To be able to use that computer. How do you understand what the machine is saying? How do you set up the program? How do you set up the tool? If at all there is human intervention required, that is where you will require the skill, and not as in to be able to manage the operation, because the computer is controlling the operation, the CNC machine is controlling the operation, we are just monitoring it. That skill is what is required. So in that sense we can say low skill requirement, isn't it? Otherwise you have to have a knowledge of how should we operate the machine, isn't it? That is why I raised that point. That is that correct? So in one sense, yes, right? So fewer personnel, right? Because computer software controls the machinery, fewer technicians are needed for operation and oversight, cutting overall expenses. So you need not have more workers because the computer is taking in charge. So that, and flexibility, the software can be reprogrammed quickly and easily to produce different parts, allowing operations to keep up with shifting customer demands. So you see, when there is a change in the product design, when a different product comes in, one product came in, okay, one batch of 30 components, let's say, another batch came in. So all that is required is you have to change the program, right? Reprogram it. So that is quickly, that can be done quickly. So that in that sense we can have flexibility. The CNC machine is flexible in the sense that it can handle different products which are having different designs. So customer demands, if there are changes in the demands, suddenly a product A demand has increased. So all you need to do, you are continuing with product B. All you need to do is have the program for product A. So like that, right? And then the capability. This technology uses computer precision to go beyond the limitations of manual capabilities. More complex and integrated operations are possible with CNC machine. We have seen, right? Is that turbine, what we are producing, that small turbine blade, you see how difficult it is, right, to do it manually. So the capability is also there, is another advantage that you get, that the machine is capable of producing complex and intricate objects, right, beyond the limitations of manual capabilities. Clear?
Clear, sir.
Yes. Okay. So then the disadvantages. Cost. They are more expensive, isn't it? Costing like in lakhs, right? So CNC machines are more expensive and require a greater initial investment than machines that can be operated manually. However, as this technology becomes the standard, supply is increasing, resulting in cost gradually decreasing. So more and more machines are being produced. So, and also the technology as it develops, you have uh, decrease in the prices also, some sort of decrease in the price, because the same machine can be produced efficiently with less cost.